Ever wondered what makes a nuclear bomb so incredibly powerful? The answer lies deep within the realm of atomic physics, in a process known as nuclear fission. In a nutshell, nuclear fission is the splitting of a heavy, unstable nucleus into two lighter nuclei, releasing an enormous amount of energy in the process. This energy, when harnessed and controlled, powers our nuclear reactors. But when it's unleashed all at once, it results in the devastating explosion of a nuclear bomb. The main ingredients for this cataclysmic reaction are heavy elements with unstable nuclei, such as uranium or plutonium. These elements are chosen for their properties that allow them to undergo fission when struck by a neutron, setting off a chain reaction that multiplies the energy release exponentially. So the first ingredient of a nuclear bomb is a heavy, unstable element like uranium or plutonium. This is the atomic trigger that sets the stage for the immense destructive power of a nuclear bomb. But how does one initiate this powerful nuclear fission, you may ask? It's a question that unveils the heart of the atomic bomb's operations. The answer lies in a tiny, unassuming subatomic particle, the neutron. Picture the nucleus of an atom, a tiny, densely packed bundle of protons and neutrons. Now consider a neutron, like a rogue agent, speeding towards that nucleus. It's the neutron's job to act as a trigger, a catalyst for the fission process. It's a simple action really, but one with extraordinary consequences. When a neutron collides with the nucleus of a uranium or plutonium atom, it disturbs the delicate balance of forces holding the nucleus together. The impact of this collision causes the nucleus to become unstable, and it splits apart. This process, known as nuclear fission, releases a colossal amount of energy. The energy is so vast that it makes the energy released by chemical reactions, like those in conventional explosives, seem minuscule in comparison. But there's more to it than just a simple collision. The neutron's energy, its speed, plays a critical role. Too slow, and the neutron is likely to be absorbed by the nucleus without causing fission. Too fast and it may just bounce off. It needs to be just right, a bit like Goldilocks' porridge, to successfully initiate the fission process. So the neutron is critical. But where do these neutrons come from? In a nuclear bomb, they are typically provided by a separate ingredient, often a small amount of radioactive material. This material undergoes spontaneous fission and produces the neutrons needed to start the chain reaction. In essence, the neutron is like the spark that ignites a fire. Without it, the vast energy stored within the nucleus remains untapped. With it, the nucleus splits, releasing a force capable of unimaginable destruction. The second ingredient, then, is a source of neutrons to trigger the fission. This simple subatomic particle, when introduced at the right speed and in the right quantity, becomes the key to unlocking the formidable power of the atom. What happens once the fission process begins? Well, the magic, or rather the physics, lies in something called a chain reaction. Picture it like this. One neutron strikes a uranium atom, causing it to split. This releases energy and, importantly, more neutrons. These freshly released neutrons then go on to strike other uranium atoms, causing them to split, releasing even more energy and yet more neutrons. This process repeats itself, escalating rapidly. Each fission event triggers more fissions and so on and so forth. This chain reaction is the heart of a nuclear bomb. It's what unleashes that vast destructive power. But it's not as simple as just starting the reaction. The bomb's design plays a critical role in making sure this chain reaction can continue unimpeded. Think of the bomb as a carefully constructed stage designed to keep the spotlight firmly on our actors, the uranium atoms. The design must ensure that the neutrons produced in each fission event have a high chance of causing further fissions rather than escaping into the environment. This is achieved by using a dense, heavy material such as uranium or plutonium and shaping it in a way that encourages neutrons to collide with other atoms instead of escaping. Moreover, the design must also consider how to initiate the chain reaction at the right time. This is typically done by using conventional explosives to compress the nuclear material, creating the conditions needed for the chain reaction to kick off. So, while the chain reaction itself is a natural process, a consequence of the inherent properties of certain heavy elements, making it work in the context of a bomb requires careful engineering and a profound understanding of nuclear physics. The design of the bomb, then, is another crucial ingredient. Now, how do you deliver such a powerful weapon to its target? The answer lies in the delivery system, an integral part of a nuclear bomb's design. It's not enough to just create a nuclear bomb, it has to be transported to its intended location, and this is where the delivery system comes into play. Delivery systems for nuclear bombs have evolved over time, with technology playing a significant role in their development. Initially, during the early stages of nuclear weaponry, airplanes were the go-to delivery system. The bomb would be loaded onto a bomber aircraft which would then fly over the target and drop the bomb. This method, however, had its limitations as it depended on the range of the aircraft and was susceptible to anti-aircraft defenses. With advancements in technology, the delivery system for nuclear bombs was revolutionized with the advent of ballistic missiles. These missiles could travel at extremely high speeds and over long distances, delivering the nuclear payload with precision. Intercontinental ballistic missiles, or ICBMs, can even traverse continents, making any part of the globe within their reach. Submarines also serve as a delivery system, capable of launching nuclear missiles from underwater. This provides a stealthy approach, making it difficult for adversaries to detect and counteract. Modern delivery systems also include cruise missiles, which can be launched from various platforms such as ships, submarines, and aircraft. These missiles are designed to fly at low altitudes, evading radar detection, and can be programmed to follow specific routes, ensuring accuracy and effectiveness. But it's not just about getting the bomb to the target. The delivery system also has to ensure the bomb detonates at the right time and place. This requires intricate design and engineering, making the delivery system a complex and critical component of a nuclear bomb. In essence, the delivery system is not just a means of transportation for the bomb, it's a sophisticated piece of technology designed to ensure the bomb reaches its destination and detonates as planned. It's a testament to human ingenuity, though a grim one at that. The delivery system, then, is another key ingredient of a nuclear bomb. So what makes a nuclear bomb so devastatingly destructive? Well, the answer lies in the massive energy release that occurs during a nuclear explosion. The energy release is so tremendous it's hard to fathom. To give you some perspective, the energy unleashed by a single nuclear bomb can be equivalent to millions of tons of TNT. That's like detonating all the explosives used in World War II, and then some, in a single instant. This vast energy release translates into destructive power in a number of ways. First, there's the blast wave. This is a wave of intense, high-pressure air that moves outward from the explosion point at supersonic speed. The blast wave can flatten buildings, overturn vehicles, and cause severe injury or death to people caught in its path, even miles away from ground zero. Next, there's the heat. The temperatures at the core of a nuclear explosion can reach into the tens of millions of degrees. This intense heat can ignite fires, melt steel, and cause severe burns. Even people and objects some distance away from the blast can be set ablaze by the thermal radiation. Finally, there's the radiation. Nuclear bombs release large amounts of ionizing radiation, which can cause radiation sickness or death. This radiation can also contaminate the environment, making areas uninhabitable for years, decades, or even centuries. It's important to remember that these effects aren't isolated. They interact and amplify each other, creating a web of destruction that extends far beyond the initial blast. The blast wave can spread fires ignited by the heat, for example, and the radiation can poison people and animals trying to escape the destruction. The immense destructive power of a nuclear bomb, then, isn't just about the energy it releases. It's about how that energy is converted into different forms of destruction, blast, heat, and radiation, that work together to cause widespread devastation. The final ingredient of a nuclear bomb, then, is the immense destructive power it unleashes. So there you have it, the main ingredients of a nuclear bomb. We've taken a deep dive into the elements that make these devices possible, starting with heavy elements such as uranium or plutonium. These elements, when struck by a neutron, undergo fission, releasing immense amounts of energy. The design of the bomb plays a critical role in allowing this process to continue in a chain reaction, releasing a burst of energy that is both awe-inspiring and terrifying. But it's not just about the ingredients and the reaction, it's also about the delivery system. This part of the bomb ensures that the device reaches its target before the reaction is initiated. Ultimately, we arrive at the destructive power of the bomb, a force so potent it can level cities and change the course of history. But let's not forget, while the power of the atom can be used for destructive purposes, it's important to remember that it can also be harnessed for peaceful uses like generating electricity. The choice is ours.